the information about ionic compounds because this is an ionic compound, okay? And so if it's ionic, then it's going to form the aqueous ions. So whenever you see an ionic formula and there's a molarity of it, that means that it has been dissolved. A thing's a solution. And so the first thing you do is split it into ions. So there's one format that I want you to use, and that is you write the formula of your ionic compound. And this thing is all aqueous because it's already dissolved. And then you're going to, because it's a solution, I'm going to do the one-way arrow, and over it goes the water. So for ionic compounds, remember that water is just the solvent that breaks the ionic bond. You don't put plus water. Okay. So for the ionic compound, it is going to split into its cation, which is sodium. And then the rest of it is the anion. So HSO3, and that would be -1 because sodium is +1 and it's a 1-to-1 ratio. So if it's an ion that you don't recognize, you can see what the charge of the cation is to figure out the anion. Okay. So this in water is the sodium ion and the hydrogen sulfite ion. So then you look at each ion to decide if it does something to create hydronium or hydroxide. So our positive ion is sodium. It is a group 1A metal cation. It does not affect the pH. And so we don't need to worry about the sodium. So this would be no effect on the pH. Okay. Then we have the HSO3 -1. So these are the previous anions. We have hydroxide. It is not hydroxide. It is not one of these 8 that have no effect. And so it is an anion that will affect it. So most of them fall in the category of it's a weak base. Most anions are weak bases. But then there's the special one, and I put it over here. So if the anion has hydrogen, then the hydrogen could be lost and it act like an acid. Because if it has a hydrogen, it has the potential to lose it like an acid would. Or if it has a negative charge, it has the ability to be a weak base. So it can be both. And so we want to show it acting like an acid, and we want to show it acting like a base, and then compare and see what it's most likely to do in water, like its behavior in water, which one's better. And so I'm going to write the acid dissociation, and then it would have a Ka if it acts like that. And then I'm going to write the base dissociation, and it would have a Kb. So here, acid dissociation. So you always put the chemical that has dissolved. And now we need to put plus water because we want to show how it behaves in water by giving hydrogen to water. And so it will create its conjugate base and hydronium. This is its acid dissociation. It's weak, so it has equilibrium arrows, and since it's weak, it will have a Ka value that we're going to find in Appendix H. So this is the chemical right here that we want to find in Appendix H. So in Appendix H, if you look up, this is under sulfurous acid, you should find HSO3 -1. And the value in OpenStax Appendix H for HSO3 -1 is 6.4 times 10 to the -8. So if it's a weak acid, it will have a Ka value. This is not the expression. This is just the value of the constant. It's the Ka part. The The other side is the concentration of all of the ions at equilibrium. Okay. So this is what we did first. We did the weak acid dissociation and we looked up the Ka in Appendix H. Appendix H meaning OpenStax Appendix H. Now we're going to do the weak base dissociation and we're going to calculate the Kb using the conjugate acids Ka. So if this ion, instead of giving up a hydrogen, adds a hydrogen, that would make it be a base. So if something's a base, it will accept a hydrogen. So it will form its conjugate acid. And so we just add a hydrogen to this formula, and that gives us H2SO3. And it forms hydroxide. So this is the conjugate acid. So if it acts like a base, then when this ion is dissolved, it's going to interact with water and take a hydrogen away from it and form sulfurous acid and hydroxide. Base dissociation reaction there. This thing, because we want its base behavior, it would have a Kb value. Kb. So its Kb would be how it acts as a base, the number. That the value of Kb depends on its conjugates Ka. So it is important when you have a base that is dissolved that you write the conjugate acid on the other side, and then you want to label it as a conjugate acid because this will take you down the pathway of I need this thing's Ka. So I'm going to put right next to conjugate acid, I'm going to put Ka equals. Because my little diagram that I created for the little flow chart is you need to look in Appendix H for the conjugate acids Ka. So this conjugate acid, its Ka is 1.6 times 10 to the negative 2. So that is not the Kb. This is the acid that it would be in equilibrium with. So in order for this thing to act like a base, it has to be strong enough to be able to be in equilibrium with this thing. And so the K values, this is kind of a measure of the constants. Like they're competing with each other because they're in the same equilibrium. So to figure out the Kb, its ability to be a base, you use the formula Ka times Kb equals Kw, which is 1 times 10 to the negative 14. But these have to be conjugates. And so the Ka is the Ka for H2SO3. And that would give us the Kb of HSO3. So this value, we just looked it up. To rearrange it each time, you're going to divide both sides by Ka. So 1 times 10 to the negative 14 divided by 1.6 times 10 to the negative 2. This is going to be a very small number because the top is negative 14, the bottom is negative 2. So 1 EE negative 14 divided by 1.6 EE negative 2. 6.25 times 10 to the negative 13. So here's what we have done. We had our ionic compound and we split it into cation, anion. and we were able to ignore the cation because it's not going to affect it. But we had to do a bunch of work for the anion over here. We had to look at it as an acid and look at it as a base. And now we want to compare its ability, which is wrapped up in Ka, to be an acid versus its ability to be a base, which is wrapped up in the value of Kb. So our numbers are 6.4 times 10 to the negative 8 for Ka versus 6.25 times 10 to the negative 13 for Kb. So which is bigger, the Ka value or the Kb value? Ka is bigger. So when this thing dissolves in water, it ends up with a bigger Ka value, which means it is most likely to behave as a acid. So again, the constant, it is a numerical way to represent how good it is at losing a hydrogen or gaining a hydrogen in water. And so it has a much bigger ability to lose a hydrogen. So this equilibrium in water is more stable for it than this one. So this is the one that we are going to use. So complete the process to determine. So what this means is once you decide which of these ways is the behavior of it, then you're going to take that dissociation and you're going to put it into a rice chart. So that's what I have right here. So we've already eliminated sodium. So don't put sodium back on it. So we're just going to copy our acid dissociation. So we decided that it was a weak acid. And so we're going to do the acid dissociation that we wrote on the previous page. So now we're actually ready to start the process, which is write out the reaction and then write the expression. So it's a Ka because we said it was an acid. So that's products over the reactant, which is our chemical. So we're writing how it behaves as a reaction. And so this is the conjugate base and hydronium divided by the weak acid that dissolved. That's always going to be the equilibrium concentrations positions, because if it's an acid, it will create a conjugate base and hydronium. And it will have a constant that's Ka. Then you just plug in the information into the chart, just like we've done before. So the concentration of this chemical is 1.5, 0 molar. And we don't have any sulfite or hydronium to start with. Since it's weak, we don't know how much dissociates. So the change is just X. So at equilibrium, there'll be 1.5 minus X of our chemical that's dissolved. And we'll have X amount of sulfite and X amount of hydronium. Then you just plug in the concentrations on the concentration side and the constant on the constant side. So the constant that we found was 6.4 times 10 to the negative 8. And that equals X times X over 1.5 minus X. So when you get all of the information, which includes the correct constant and then all the equilibrium concentrations, then you can ask yourself, can I ignore that minus X? Yes, because our constant is to the -8 power. And so I'm going to circle this and cross it out. So my denominator now, when I do the math, can just be 1.5. So I'm going to multiply that by the constant. And that will equal X squared. And then we do the square root of both sides. So X is 3.10 times 10 to the -4. And if you go back to all the examples, whether it's you wouldn't be able to look at the ICE part of the rice chart and know if it's an acid or base, because all of the thing, or if it's an ion or a molecule, you would not know, because all of the charts for acids and bases that are weak look just like this: the concentration minus X, and then 0 plus X, 0 plus X. They all look the same because all you're doing is moving one hydrogen off of that substance. Then we solve for X. What we're looking for, again, our goal is to find hydronium, which is going to be X for acids. So because that is an acid, our hydronium concentration equals 3.1 times 10 to the -4 molar. So our goal is to get hydronium so that we can use the predicted hydronium concentration to calculate pH. So then you take pH equals negative log of the hydronium concentration. And you get 3.51. Very last thing is you want to compare your pH with what we predicted. We didn't predict the pH. We predicted that it was going to be a weak acid. So all of the work on the previous page was just to figure out it's an acid. Then we did all this work and we found X, which was hydronium. And then I did the negative log and got 3.51. And you want to just double check and make sure that that is a pH of something that was like a weak acid. So acids are always going to be below what number? 7. And the closer to 0 it is, the more hydronium there is. Weak acids, no matter what the concentration, are not going to have a high concentration of hydronium. So 3.51 is like halfway to 7. And so, yes, this is acidic. So we're on the right side of the pH scale. And it's not really low, which it shouldn't be because our constant is so tiny. And our concentration of hydronium is small. So all of it kind of matches.